The following question 5 on the review for PDE says, let a be greater than 0 be given. Find a function of u satisfying u of r and theta equals the infinite sum from n equals 0 to infinity of a sub n r to the n p sub n of cosine of theta, with the condition that u of a comma theta is equal to 1 plus 2 cosine of theta. For theta between 0 and pi, where p sub n of x denotes the nth order Legendre polynomial. So the first thing we're going to do is go ahead and plug in a for any time we see it r, and we'll just try and imply this initial condition. U of a and r, u of a and theta is equal to 1 plus 2 cosine of theta, and that's equal to the infinite sum from n equals 0 to infinity of a sub n times a to the n p sub n of cosine of theta. Now, the way we're going to solve for the coefficient a sub n here is a little bit tricky. So we want to imply the orthogonality of Legendre polynomials. And we also want to be careful because we're going to be integrating, like we're trying to get to a form p sub n of s ds, p sub n of s ds squared, and from -1 to 1, because we know this form has the solution 2 over 2n plus 1. So the way we do this, we multiply both sides by p sub n of cosine of theta and sine of theta. And the reason we do sine of theta is because the derivative of cosine is negative sine, and we're going to do a u substitution, and we want the negative to stay because we're going to be flipping the bounds. So let me just show you what we're going to do. Multiply by that, and then we're going to integrate both sides. Sounds good? So if we multiply by that on both sides, we get an integrate. We get the integral from 0 to pi, the bounds for theta of 1 plus 2 cosine theta multiplied by p sub n of cosine theta multiplied by sine of theta. And this is equal to the infinite sum, and this is d theta, equal to the infinite sum n equals 0 to infinity of a sub n, a to the n, multiplied by the integral from 0 to pi of p sub n cosine of theta, multiplied by p sub n of cosine theta, multiplied by sine of theta, d theta. Okay, so I'm going to go ahead and use change of variables, or s substitution in this case. We're going to let s equal cosine of theta, and that makes ds equal to negative sine of theta, d theta. And using these bounds, cosine of theta at 0, cos of 0 equals 1, cos of pi equals -1. So we get the integral from 1 to -1 of 1 plus 2s p sub m of s multiplied by sine of theta d theta. We divide by sine of theta d theta to get our ds, and we get a negative out front, and we get d theta over here, not d theta, ds. And what this negative sign does, it flips the bounds. We get -1 to 1 of 1 plus 2s p sub m of s ds. Now let's apply the same thing over here. We're going to go ahead and get the integral from 0 to pi p sub n of cosine theta multiplied p sub m of cosine theta times sine of theta d theta. Going and doing that, change of variables, we get -1 to 1 of p sub n of s multiplied by p sub m of s ds. So these are orthogonal if n does not equal m. They're orthogonal, so it would go to 0. If not, if m was equal to n, then we have the integral -1 to 1 of p sub n of s squared ds. And like I said up here, this is a form that we know the solution to. So we have a sub n, a to the n, and this infinite sum n equals 0 to infinity. This is all equal to, and it's not an infinite sum anymore because we choose n equal to n. So it's just one term, and it's going to be equal to this integral on the other side, -1 to 1 of 1 plus 2s times pm of s ds. And so this bit over here is 2 over 2n plus 1. And let's go ahead and make this p sub n because n is equal to m. We get this is that integral, and then a sub n times a to the n So if we move this to the other side, we get a sub n is equal to 2n plus 1 over 2a to the n multiplied by this integral negative 1 to 1 of 1 plus 2s p sub n of s ds. All right, so now that we're here, we want to find what this integral gets us. So a sub n is going to be equal to 2n plus 1 over 2a to the n multiplied by the integral from negative 1 to 1 of p sub n of s. And this 1 we can represent as p sub 0 of s, because p sub 0 of s is equal to 1. And then this 2s is equal to 2 times p sub 1 of s. So we get p sub n of s times p sub 0 of s ds plus 2 times the integral negative 1 to 1 of p sub n of s times p sub 1 of s ds. So now these two things are orthogonal if n doesn't equal 0, meaning they're 0. And if n doesn't equal 1, these are orthogonal. So we're going to have two coefficients for a sub n. So a can be equal to 0 and a can be equal to 1. Or n can be 0 and n can be 1. So we get 2 times 0 plus 1 over 2 times a to the 0 times the integral of p sub 0 of s ds squared. And over here, we get 2 times 1 plus 1 over 2 times a to the 1 multiplied by the integral. These two integrals are negative 1 to 1 still, of p sub 1 of s squared ds. And so these two integrals work out to be 2. A sub 0 equals 1/2 times the integral of p sub 0 squared of s ds. So remember, this solution comes in the form 2 over 2 times n plus 1. So this is going to be equal to 2. 2 times 1/2 equals 1. So a sub 0 equals 1. And then a sub 1 is going to be equal to 2 times 1 plus 1 over 2a. And oops, I forgot. So look, I forgot this 2 right here. So there's a 2 out front of this integral still. And this is equal to 3 over 2a multiplied by the integral negative 1 to 1 of p sub 1 of s ds, and this is squared. And this p sub 1 of s ds squared gives you, so we've got a 2 over here still. This gives you 2 over 2 times 1 plus 1 equals 2/3. So we get a sub 1 equals 3 over 2a times 2 times 2/3. So these 2's cancel, these 3's cancel, and we get 2 over a. Now the infinite sum is from n equals 0 to infinity. So u of r and theta equals this, and it's a sub n to the r multiplied by r to the n times p sub n of cosine theta. And we solve for a sub n, there's only 2 of them. So this sum reduces to a sub 0 r to the 0 times p sub 0 of cosine theta plus a sub 1 times r to the 1 times p sub 1 of cosine theta. Or we can write it, we said this was 1. 1 times r to the 0 is 1 times p sub 0 of cosine theta. So p sub 0 of s is equal to 1. So p sub 0 of cosine theta is equal to 1. So this whole term becomes 1. And then we have a sub 1, which we said 2 over a. And then we have r to the 1 is r. And p sub 1, so p sub 1 of s is equal to s. So p sub 1 of cosine theta equals cosine theta. And we have our solution. U of r comma theta equals 1 plus 2 over a r cosine theta. And you could do an easy transition into Cartesian coordinates. This r cosine theta becomes a x. And you got to remember we're still on like a circular domain. So yeah, I'll pop up a picture of what the solution looks like. But pretty cool stuff. Thanks for watching.